Hello guys, welcome to our physics class for today. Today we are going to be looking at elastic properties of solids. Elastic properties of solids, and it has to do with Hooke's law. So this is Normal Science Tutors Online. You are welcome to our physics class for today. Please, if you have not subscribed to this channel, please, what are you waiting for? Please subscribe to this channel. Click on the notification bell so that whenever we upload a new video, YouTube will notify you. Also, please, if you like what we are doing, give us a like, give us a thumbs up. Then please also subscribe. You can also invite your friends to come and enjoy this physics class that we are bringing direct to your homes. Then if you have any challenge, you can reach us via the WhatsApp number that is showing right on your screen. I remain Untitled Michael, and as I've always said, I hope you have your writing materials ready with you so that we can go straight to our class for today. So we are looking at Hooke's law and elastic properties of solids. So please, if you are ready, let us go straight to our class for today. Okay, so when you are talking about elastic properties of solids, you are looking at either the formation or extension of materials. So you know that when a force is applied to some materials, it could either tend to extend them or deform them depending on the nature of the material. So elasticity is the ability of a substance to regain its original shape and size after being distorted by an external force. It's just like your rubber band. If you stretch your rubber band, if you don't overstretch it, if you release it, it will return back to its original length, right? The same thing applies to spring. If you extend a spring up to an extent, it can return back to its original shape or original length. Alright, so that ability for the substance to return back to their original shape or size is known as elasticity. So elastic material is the substance that can regain its original shape and size after being distorted or after a distorting force is removed from it. Okay, so that is an elastic material. Any material that when you stretch or you try to compress and it returns back to its original shape is known as an elastic material. Okay, and the law that governs this behavior of materials is known as Hooke's law. That is a law. It is the Hooke's law that governs this behavior that we just discussed now. Now, what is the statement of the Hooke's law? The Hooke's law states that provided, take note, that the elastic limit of an elastic material is not exceeded, the extension or compression. Take note, when I am using extension, but it also means compression. So the extension or compression of the material is directly proportional to the load or applied force. This is the Hooke's law. The extension or compression of the material is directly proportional to the load or applied force. Now, mathematically stated, it means that force is directly proportional to E, which is the extension or compression. Now, the constant of proportionality is equals to K. And so when you make K the subject of the formula, it becomes force or load over extension. And we know that the unit of force is the Newton, and the unit of extension is the length. Is that okay? So which means that the unit of K is equals to Newton per meters. Now, this K has its own meaning. Okay, so we say that F is equals to load or force, and E is the extension. That's what we just said. Then the K is known as the force constant of the material. So the K is either you can also say it is the force constant, right, or the stiffness or the elastic constant of the material. Okay, so that is the K. K, you can call it force constant, elastic constant, or stiffness of the material, and this is the unit of K. Okay, now this Hooke's law can also be represented in a graph, and that is what we're going to discuss in the next slide. So okay, so just as I said, the Hooke law can be represented on a graph. Now this first graph here depicts the normal Hooke's law, that extension is proportional to the load, or load is proportional to the extension, as the case may be. This particular graph obeys the Hooke's law. Now for these other two graphs, this graph obeys the Hooke law, and this one also obeys the Hooke law up to the P, up to point P. These ones obey the Hooke's law up to the point. This is extension over load, and this is load over extension. Now these two graphs obey the Hooke's law down to point P, but beyond the point P, the Hooke's law, it doesn't hold again. The Hooke's law does not hold again. So according to Hooke's law, from point O to point P, the material obeys the law, and point P is known as the point of, or is known as proportionality limit. Okay, so you can see that it is only from O to P that you have a straight line graph like this. So that is why it is called the proportionality limit. Okay, then point E is known as the elastic limit of the material. This point E is the elastic limit of the material. Okay, so at this particular point, the material it can still return back to its original shape. That is, between this point, the material can still return back to its original shape. Okay, so this point O to E is known as the elastic region. It is known as the elastic region, and the elastic region of the material is the point where, once the elasticity or the deforming force goes, if the material extends beyond point E, it does not return back to its original point again. So beyond point E, the material does not return to its original shape. Point Y is the yield point. At this point, the material has lost all its elasticity, so it cannot go back even. Yes, at point Y, the material has lost all its elasticity. Then point B is the breaking point. This breaking point means any further application of force, the material can just snap and break up. The material will just snap and break up. Okay, so these are the meanings of these various points that are on this load over extension graph, or this extension over load graph. And it's good that you know them, because sometimes they give you this equation, this graph, for you to interpret. So this first point is proportionality point, is elastic limit, this is the yield point, and then this is the breaking point. Okay, so I will explain those points further. So the elastic limit is the limit of force beyond which the stretch wire does not return to its original length when the stretching force is removed. So what that simply means that up to the elastic limit, the elasticity of the material still holds. That is, up to that point E, the material will return to its original length when the deforming force is removed. But beyond the elastic limit, the material loses its elasticity. I think that's what I've just discussed before. Beyond that point, the material loses its elasticity. Okay, then the yield point is the point beyond the elastic limit, in which the elastic material has yielded all its elasticity permanently and it has become plastic. So at that yield point, the material has become plastic. Then the breaking point is the point of maximum extension, where the material reaches its maximum extension and may finally snap or break. So these are further explanation to what I just mentioned previously. Is that okay? So these are further explanation to it, and it is good that you understand those points. Okay, it is good you understand them. Then you can just even, if you have a spring and you try to extend it, you will see that the more you are applying force, at a point in time the spring will not return back to its original shape. Then the further you stretch the spring, at a point the spring can just break or snap. Okay, so these are what the Hooke's law covers, and these are what we are discussing in our class for today. So beyond that, we still have other physical properties that we need to discuss in this Hooke's law, and that is stress and strain. That is stress and strain. Okay, so if you have L as the length of a wire and E as the cross-sectional area, which is measured in meters squared, and L is measured in meters, and then the extension of the material is given to you to be E, and it's measured in meters, and there's a force that is extending the material that is given to you as N. Now, the ratio or the force to area is known as a stress or tensile stress of the material. So stress is equals to, just know that stress equals to force over area. Okay, so the material can be a circular material, so that's why you have this pi radius square. The area of a circle is pi radius square. So it can also be a linear material or a normal regular shape, which will give you a, so the area of the material, force all over the area of the material, is known as stress, and the unit of stress is the unit of force and that of area, which is Newton per meter squared. Okay, so stress is equals to Newton per meter square, and that is force over area. So beyond stress, you also have what is called strain. Strain is the ratio of the extension to the length of the material. The ratio of the extension to the length of the material. So that is strain or tensile strain of the material. So tensile strain is given to you to be equals to extension or compression all over length. Extension or compression all over length. That is your strain. So if you look at strain, you find out that extension, the unit of extension is meters, and the unit of extension is meters, and the unit of length is also meters. So which means that strain does not have a unit. Is that okay? And don't forget that extension E is equals to final length. Let me put, if final length is L1 minus L0. So L1 is final length and L0 is equals to original length. Okay, so that is L1 minus L0. So this is L1 minus L0. Okay, so that is what is extension. So as I've said, the strain does not have any units because the units of extension or compression and length, they are the same. So strain does not have any unit. Okay, so that is tensile stress and tensile strain. Tensile stress is force over area, and tensile strain is equals to extension over length. I hope this one is clear. So according to the Hooke's law, we are going to describe another physical property that we need to know, and that is the Young modulus. So according to the Hooke's law, the Hooke law states that stress is proportional to strain provided elastic limit is not exceeded. Stress is proportional to strain provided elastic limit is not exceeded. So mathematically stated, stress is proportional to strain, and the constant of proportionality is called the Young modulus. The concept of proportionality, this y here is known as the Young modulus. So mathematically, Young modulus equals to stress over strain, and we already know that the equation for stress is force over area, and that of strain is extension over length. Okay, so if you write this one out, you are going to have that Young modulus equals to force times length all over area times E. You know, this equation, you can write it like this. This is F over A, right, divided by E over L. So this is same thing as F over A multiplied by L over E. Okay, your normal simple mathematics. So this gives you F times L all over E times E. Okay, so that is exactly what we have here. That is what we have here. So if you look at it, you find out that the unit of Young modulus is the same thing as the unit of stress, or the unit of tensile stress. Since strain does not have any unit, then the unit of Young modulus is the unit of stress or tensile stress. Okay, so I hope this is clear and this is understood, right? So if you understood this, we'll now go straight to solve some problems on this particular topic. But before we solve problems, I still want us to talk about the work done in a spring or elastic material. Work done in a spring or elastic material. So if, assuming an applied force F caused an elastic spring of length L to undergo an extension or compression E, then the average force will be initial force minus final force all over 2. Or initial force, so plus, that is average force, initial force minus final force, initial force plus final force all over 2, right? So that this can now be written as this, sorry for that. Okay, so this can now be written as this, that initial force plus final force all over 2. So that gives you F is equals to 0 plus final force all over 2. This is your initial force and this is your final force, all divided by 2. So this cannot be written as this. Now work done is given to us to be force times distance, and that is average force times extension. Alright, so that is average force times extension, and when you bring this value for your average force to here, you have work done is equals to half force times E. So this is the first equation that you need to take note of. Can put it as equation 1 for work done in a spring or elastic string. Then note from the Hooke law, we said that F is equals to KE is equals to force constant times the extension. So if you substitute this into this equation, equation 1, you will have work done is equals to half KE squared. KE squared. So this is equals to your second equation for this. This becomes your second equation. Work done is equals to KE squared. So work done, so this one is the work done by a spring when compressed or extended by a force. So this work done is also known as the energy stored in a string. Okay, so the energy stored in a string is also equal to the work done. And you know that the unit of work is joule already. Okay, so these are the basic equation that you need to take note of when you are talking about energy stored in a string or work done in a string. Alright, so these are the basic questions for you to take note of. We are going to solve some problems now to drive home all the points that we have discussed so far, so that you have a better understanding and how to use these equations to solve different problems when it has to do with elastic properties of solids. Okay, so we'll go straight now and solve some problems. So we have two questions here. There are more questions. Okay, so these are the first two questions I want to look into. This one says that a force of 0.8 Newton stretches an elastic spring by 2 centimeters. Find the elastic constant or stiffness of the spring. So from what we discussed just now, we said that given that F is equals to KE. Okay, K, which is the force constant or stiffness, equals to F over E. So here we are giving F to be 0.8 Newton and E extension is 2 centimeters. So you have to convert the 2 centimeters to meters. You divide it by 100 to give you 0.02 meters. Alright, that is your E. Then your F is already given to you to be equals to 0.8 Newton. Okay, so when you input all those informations into this equation, you are going to have 0.8 all over 0.02. So by the time you work this out, you will have that your stiffness of force constant equals to 40 Newton per meters. Okay, I think this is relatively simple, right? Just direct to the point. This is simple and direct to the point, and this is how you use this formula to solve problem. You only need to understand what is extension and what is force. Okay, so this is another question. Say an object weighing 0.6 Newton is hung on a spiral spring and causes it to extend by 6.0 centimeters. The object is removed and a block of wood replacing it causes the spring to extend by 10 centimeters. What is the weight of the block of wood? Okay, so here you are given that the weight, the force or the initial weight of an object is equals to 0.6 Newton. It causes an extension of 6.0 centimeters, and this 6.0 centimeter, when you convert it to meters, it will be equals to what? 0.06 meters. Okay, so from this our first equation, we are given that F is equals to KE. So what you first of all do in this kind of problem is to find the force constant, and the force constant of this spring is equals to F over E, and all those ones will be given to you. F is 0.6 and E is 0.06. So if you work this out, you will get the force constant of this spring to be 10 Newton per meters. Okay, so since this is the same spring that this block of wood is replacing, then the force constant of the string remains the same. Okay, so from here we can now find the width of the block of wood, because they said that the block of wood gave the system or the setup an extension of 10.0 10.0 centimeters. So the width of that one So if the extension it gives, extension is equals to 10.0 centimeters, this is equals to 0.1 meters, and we are told from our equation that force, which is equals to weight, equals to Ke. Now from our initial solving, we've gotten the value for K, which is the force constant. E is equals to 0.1 meters as we have solved. So you just multiply K times 0.1. So this will give you the weight. This will give you the weight. So when you multiply that, you're going to have the weight of the block of wood to be 1.0 Newton. Okay, so because weight is also equals to force, so the weight is equals to 1.0 Newton. Okay, so you must, for any spring or any elastic material, you must look for the force constants. So like for this equation now, the force constant was not given to you, so you have to look for it before you can find the weight or the force. Okay, so I hope this one is also clear. Let's go to another question. I have about 8 questions to solve here before I give your test listing, so we'll be going gradually. All right, so these are the first two. Let's go to the third one. So this is another question that we have to look into. It's another question. This one says that a force of 2 newtons stretches an elastic material by 30 millimeters. What additional force will stretch the material 35 millimeters, assuming that the elastic limit is not exceeded? So this question is almost like the one I just solved, the question number 2. Okay, so here they said that a force of 2 newton stretches the material by extension by 30 millimeters. So you have to convert this to meters, and that means you have to divide it by 1000. Millimeters to meter is 1000. So when you make this division, it will give you 0.03 meters. Okay, then force from my equation of from the law, Hooke's law, force is equals to Ke. So K is equals to, as I said, you must find K, the force constant of the material. So K is equals to force over extension. So in this case, it's 2 over 0.03. So if you work that out, sorry, that 3, let me write it properly so that okay, so if you work this out, you will have that the force constant is equals to 66.7 Newton per meters. All right, that is 66.7 meters. Okay, so this is your force constant. All right, so just as we did for the first one, we also do this just as we did in the previous question. Now that you know the force constant, you can now find the value of the force that will extend this string by this 35 millimeters. So you convert this 35 to also meters. All right, so that gives you 35 all over 1000, and when you divide that out, you have 0.035 meters. So I haven't done that. From Hooke's law, force is equals to Ke. So substituting into this equation, you already have the value of K, you have the value of E here. So this is your K and this is your E. So when you substitute, you have K, that is 66.7 multiplied by 0.035. So by the time you work that out, you're going to have 2.3 Newton. So the question is, what additional force will stretch the material 35? Already you have this force of 2 Newton. So which additional force do you need now to stretch the material by this? So the additional force is the difference between this force and this. Okay, so additional force F is equals to F2 minus F1, which is equals to 2.3 minus 2.0 is equals to 0.3 Newton. So the additional force that you need is equals to 0.3 Newton because this force is already there. So they say, what additional force do you need to stretch the string to this level? So this is the additional force. It's not this. The additional force is different between this final force and the additional force. Okay, so you need to take note of such questions. Okay, let's move further to other ones. Okay, here I have two questions. It's question number 4 and 5. The first one says that the energy contained in a wire when it is extended by 0.02 meter by force of this is what? So this is a jam question actually. So we said that energy or work done, energy is equals to work done is equals to energy, and that is equals to we said that is equals to half F E. Okay, so here you are giving the extension and this is the force, because this question is direct, it's an objective question, so just substitute values to that. Okay, half 500 multiplied by 0.02. So if you work this out, you just have that the energy or work done is equals to 5 joules. This one is very direct, it's equals to 5 joules. That's your answer for that. Okay, so this is the equation and that is how to apply it. All right, then the next one, this one says that if the stress on a wire is 10 raised to power 7 and the wire is stretched from its original length of 10.0 centimeter to 10.05 centimeter, the Young modulus of the wire is what? Okay, so this one, because it's a jam question, it requires that you understand what Young modulus is. Okay, so what you're going to do here first is to, what is the extension? Okay, what is this? They've already given you the stress. Know that Young modulus Y is given to you to be what? Stress all over what? Strain. Okay, so stress has been given to you already. Stress has been given to you already. So what you are looking for first now is a strain. So strain is equals to what? Strain is equals to extension all over length, and extension is equals to final length minus original length all over original length. That is your strain. So if we substitute into this equation, we can get our strain to be equal to 10.05 minus 10.0 all over 10.0. Okay, so from here we can get our string. So just do that that subtraction to get your string. So that will give us 0.0 0.05 all over 10. Then when you divide that out, you have 0.005. Don't forget that string does not have a unit. String does not have a unit, so this is what we'll have. So just substitute into this equation. So you have that 10 raised to power 7 divided by 5.0 times 10 raised to power minus 3. Okay. So by the time you work this out with your calculator, you have that your Young modulus y is equals to 2.0 times 10 raised to power 9 Newton per meter squared. Don't forget that Young modulus has the same unit as stress. So quite easily done, right? Because this is a jam question, you know that you have to work within less than 1 minute. So it's just for you to understand that you have to find your extension to get your string, and then you just put your value into that and you get your answer. Okay, so that is question number 5. So going further, question number 6. This question is pretty long and I want you to follow through as I solve it. It cuts across almost all the topics. Okay, so I want you to follow through as I go through this question. Question says that a spiral spring of natural length 20 cm has a scale pan hanging freely in its lower end. When an object of mass 40 grams is placed in the pan, its length is equal to 21.8 centimeters. When another object of mass 60 centimeters is placed in the pan, the length becomes 22.05 centimeters. Calculate the mass of the scale pan. Calculate the mass of the scale pan. So what I want you to know, because this is a wire question, what I want you to note is that this is a spring. So which means that the extension on the spring is brought about by the weight of the scale pan and the weight that is added to it. That is the first point I want you to know. That the extension on the spring is brought about by the weight of the pan and the weight that is added to it. Okay, so if you have that at the back of your mind, you will know that the mass that is causing the extension on the string will be equal to the mass of the scale pan plus the mass that's added to it, because here it says calculate the mass of the scale pan. That's okay. So having explained that to you, it means that the mass on the spring is equals to the mass of the scale pan plus the mass of each of the load. Let me just say mass of solid. Okay, so I'm writing this out because we are going to use this equation. We are going to use this equation to solve. Now you are giving the natural length of the spring. First of all, they give you the natural length of the spring to be 20. So if I say that is L1, it's given to you to be 20 centimeters. Okay, so when a load of 40 grams is added to it, the length becomes L2 is equals to 21.80 centimeters. Okay, so for this particular first instance, in the first instance, the mass, okay, let's just first, the extension in this case now is equals to 21.8 0 minus 20 centimeters. So if you work this out, it will give you 1.8 centimeters. This is the extension, right? So extension in the first instance is equals to 1.8 centimeters. Fine. Then in the second instance, the weight is given to you to be 60 gram. The weight is given to you to be 60 gram. 60 gram. That's the weight that is given to you, 60 gram. Yeah. Then the extension is equals to, it extended it by 22.05 centimeters. That is the new length when that weight is added. So the extension, let me say L3. So the extension is equals to L3, which is 22.05 minus 20. Okay, so if you work that out, you will have 2.05 centimeters. So far we have gotten the two extension now. The extension 1 is 1.8 centimeter. The extension 2 is 2.05 centimeters. I hope you are following. So as I've said, in the first case, in the first instance, down to this point, okay, no, down to this point, first instance, right? So first case, in the first instance, you have that the mass, as I said before, is equals to the mass of the scale pan plus 40. This is the first instance. All right, this is the first instance. And then in the second instance, say second, the mass is equals to m plus 60 gram. So this is the second instance. Now we know that according to Hooke's law, F is equals to KE. Now F is force, so F is equals to mg, mass and acceleration due to gravity, is equals to KE. Yes, F is equals to mg. So if you now use this equation, you find out that in the first instance, mass will be equals to the mass of the pan plus 40 multiplied by G is equals to K. For the first instance is not known, but the extension is known to be equals to 1.8. Okay, then so this, you can write this as your equation 1. Then for the second instance, you have m plus 60 multiplied by G equals to K. What? Your E is 2.05. So you can take this as equation 2. All right. So you have two equations already. You have two equations now already. You have equation 1 and equation 2. So from equation 1, you can make G your subject of formula, so that your G will be equals to 1.8 K all over what? M plus 40. Also, for the equation 2, your G will be equals to 2.05 K all over M plus 60. Okay, so you have equation 1, equation 2, G. So you can equate the two equations, right? So if you equate them, you have that 1.8 K all over M plus 40 is equals to M plus is equal to is equals to that is equals to 2.05 K all over M plus 60. Okay, so that is where we have. Now you can rearrange this equation. If you rearrange this equation, you will have that M plus 40 all over M plus 60 is equals to 1.8 K all over 2.05 K. Okay, so this is your rearrangement. So what you do now, you cannot cross multiply. So if you cross multiply, you will have 2.05 brackets M plus 40 equals to 1.8 brackets M plus 60. Now take note that this K, they've cancelled that already. Alright, so this is what you have as your equation. So by the time you multiply this out, you are going to have 2.05 M plus 82 is equals to 1.8 M plus 108. So all this one, you now work them out mathematically. Follow your normal mathematics procedure so that you now collect like terms. Is that okay? Just collect like terms. So you have 2.05 M minus 1.8 M is equals to 108 minus 82. So when you work this out, you have 0.25 M equals to 26. So your M is equals to 26 over 0.25. So by the time you divide this out, you are going to have 104 gram. I'm going to have 104 gram. So this gives you the weight. So that gives you the weight of the that gives you the weight of the pan. 104 gram. So if you look at this question, you find out that it takes some steps and all that it requires some basic understanding. But if you follow through, you will understand what I've said or what we have treated. Okay, so that is how to solve this kind of problem in case you come across them. This is a Y theory question actually. Alright, so let's move further. We still have some other questions to solve. Okay, so we still have some other questions to solve. Alright, this one says that a catapult used to hold a stone of mass 500 grams is extended by 20 centimeters with an applied force F. If the stone leaves with a velocity of 40 meters per second, The value of F is what? This is a jam question. Okay, so what you should know is that the work done in projecting the stone from the catapult is equals to the kinetic energy gain by the stone. Okay, so work done which is given to you by from who the equation we derived before, work done is equals to kinetic energy gained by the stone. So here you are giving mass to be 500 gram, which is equals to mass is given to you to be 500 gram, which is equals to 0.5 kg. You are giving velocity to be equals to 40 meters per second, and you are giving extension is given to you to be 20 centimeters, which is equals to 0.2 meters. So you can actually substitute all these values into this equation so that you will have that you have half F times 0.2 is equals to half 0.5 times velocity squared. Okay, so this will give you so this half can cancel this, so you have 0.2 F force is equals to, when you multiply all this one out, multiply all this out so that your answer will come out readily. Okay, so this will give you 0.2 F is equals to 800, and F, which is the force you are looking for, is equals to 800 divide by 0.2. So just work this out. So your answer will be this 4018. This will be the value of your force. Okay, so this is how to apply the equation for work done. So you see that the work done is equal to the kinetic energy gained by the stone in leaving the catapult, and it is that kinetic energy that will propel the stone to the distance that it will travel. All right, so let's take a final question. Okay, guys, we've solved a lot of problems on this topic, and I hope that you are following. I want you to spend this time so that you have a very good understanding. All right, that's why I'm spending all this time to explain what this topic. I know this topic is very critical, and you need to really understand it very well. So this question, on top of a spiral spring of force constant 500 Newton per meter is placed a mass of 5 times 10 to the power minus 3 kg. Okay, if the spring is compressed downward by a length of 0.02 meters and then released, calculate the height to which the mass is projected. This is a jam question. So this one, what you just understand is that the work done in compressing this spring is equal to the stored energy on the spring. Okay, and you know that stored energy is equals to potential energy. So what you just need to take note of is that the work done here, you are given a force constant, so the work done in compressing the spring, which is equals to half k e squared, is equals to the potential energy or the stored energy of the spring. So if you've known that here you are giving K to be equals to 500 Newton per meters, you are giving extension to be 0.02 meters. You are also giving mass to be equals to 5 times 10 raised to power minus 3 kg. So all these variables will be given to you. You know that g is equals to 10 meters per second squared. So they said height is what you don't know. Okay, so this is the formula. So if we input all this information into this formula, you are going to have a half times 500 all multiplied by the extension 0.02 raised to power 2 is equals to mass, which is 5 times 10 raised to power minus 3 multiplied by 10 multiplied by h. Okay, so you can work all this out. So if you work all this out, this will give you, if you do that, you are going to have, this will give you 0.1 is equals to 0.05 h. So you make h your subject of formula. Please work that out with your calculator. Okay, so at this level I expect that you should be able to operate your calculator well. Okay, so by the time you punch all this out, you are going to have 2 meter as your height. Okay, so that gives you the height to which the object is projected. That gives you the height to which the object is projected. Okay, so I hope this one is also simple. If you can follow through, I hope this one is also simple. Alright guys, so thank you so much. This is where we are going to stop our class for today. We've covered a lot on today's topic, and I hope you got a better understanding of Hooke's law. Alright, so thank you so much. We are going straight now to your test page. Okay guys, this is your test page. Please, I want you to solve all these problems and try your hands on all of them. How this problem we solved all of them. We solved similar questions already. So just try your hands on them and see how well you understand this topic. So thank you guys. Before I go, please guys, if you have not subscribed to this channel, please subscribe to this channel. You can see that we are doing a lot of work to put this material together. So please click on the notification bell and then give us a like. If you subscribe and you give us a like, people will know that we are doing something that is nice, and also give us positive comments. That's okay. So this is Normal Science Tutors Online. Thank you so much for your time. You can reach us through the WhatsApp number that is showing on your screen, and also under this video you can click on those links that are there. It will take you to our WhatsApp page. So invite your friends, invite your colleagues so that they can come and enjoy what you are enjoying here on YouTube. Thank you very much. We hope to see you in our next class.